Hello everyone. Today I'll be presenting the paper Risk Classification of IP Addresses Using Machine Learning with Weighted Voting Approach. This research was conducted under the State University of Ceará by Francisco Nobre, Davi Alves, myself, Ramon Araújo, Gustavo Campos, and our advisor, Professor Rafael Lopes Gomes. So this is the summary to our presentation. We're gonna have the context and motivation, which is the modern security challenge. We're gonna have the proposal, which is the solution overview and architecture. We're gonna have the methodology, which includes the dataset creation and the weighted voting mechanism. The experiments and results, which contains the machine learning model comparison and real-world performances analysis, and finally the conclusion and future work. So what is our context and motivation? We have a problem, which is the increasing sophistication of cyber attacks demanding proactive, intelligent, and adaptive security solutions. Resilient solutions capable of anticipating emerging threats are crucial for ensuring network security, performance, and availability. In our current limitations, we have the traditional approaches, such as static denial lists and manual analysis by experts, are not scalable or agile enough for the new threats. So they present significant limitations in terms of scalability, response time, and adaptability. So we have the need to develop automated solutions that use artificial intelligence to classify IP risk efficiently, scalably, and quickly. Then AI emerges as a fundamental tool for automating threat detection and classification, enabling rapid and precise responses in complex network environments. So what is our proposal? We propose a architecture to classify the risks of IP addresses that integrates a machine learning model. Our solution uses an adaptive system based on a machine learning to analyze and identify complex behavioral patterns. It classifies IPs into one of three categories, which is malicious, the deny list, trusted, the allow list, or suspicious, the suspect list. We also have the multiple threat intelligence sources. It's a new dataset was created by extracting features from 4 public threat intelligence databases, which are Abuse IPDB, Virus Total, PostDive, and IP Void. These threat intelligence databases are open sourced, freely maintained by the cybersecurity community. So it is very likely that if we have a malicious IP or a malicious hash file or some malicious activity at all documented somewhere, it's very likely that if it is in one of them, it's very likely to be in another one. And we have the multi-criteria weighted voting, which is a novel weighted voting mechanism. It's applied to combine heterogeneous data sources. This method improves interoperability and the final classification by utilizing a multi-criteria weighting strategy. So, our system architecture. Our solution operates cohesively with 3 main modules. We have the reputation check, the threat detection, and the connection management. So how does it work? We have our connection management sniffing the network for looking for TCP SYN connections, which is the very first information that is captured by a TCP connection. We use this because we want to capture the very first interaction over some malicious IP with our host. Then when we catch a TCP SYN connection, we query public databases to obtain information about a given IP, its reputation score, reports, and etc. And then when these queries return something to us, we classify them with the machine learning model. We classify the IP into one of the 3 categories: trusted, which is the allow list, suspicious, suspect, or malicious, the deny list. And then we Again, in the connection management module, we apply the rules to the firewall based on the classification. These actions include blocking, allowing, or degrading the connection, which is the TARP technique for all the suspicious IPs. So our execution flow, the process occurs in a continuous automated cycle since detection to action and reassessment. We first detect and analyze. When a new connection is detected, the system queries multiple threat intelligence databases like Abuse or VirusTotal to gain its reputation data. We classify using the machine learning model. We analyze this data to classify the IP as trusted, suspicious, or malicious, and then we act based on the classification. The firewall automatically allows, limits, or blocks the connection using the Linux firewall IP tables, updating its default tables, which are input, forward, and output, as well as the one we created, which is the trusted, suspicious, and malicious. And then we adapt. The system periodically reevaluates IP classifications to adapt to a new threat information. We do that using cron jobs, ensuring the protection is always up to date. So our data set, we collected around 2,900 IP addresses. They were collected from 4 public threat databases, and we have these features, which is the Abuse IPDB confidence score, which goes from 0 to 100. It's the confidence of malicious activity, probability based on reports. We have the Abuse IPDB total reports, which goes from 0 to 85 to 000. It's the number of malicious reports registered for the IP. We have the Abuse IPDB non-distinct users, which goes to 0 to 2 to 000. It's unique users reporting the IP, which is a credibility indicator. We have the IP void detection count, which goes from 0 to 93. It's a detection service that flags the IP as a threat. We have the risk recommended bus dive, which is critical, high, medium, low, unknown, or none. It's a consolidated risk level from multiple analyses. The virus total reputation, which goes from minus 127 to 565. It's the overall reputation. The more negative it is, it means that it has a poorer reputation. We have the virus total malicious, which goes to between 0 and 94. It's the engines classifying the IP as malicious. We have the virus total suspicious, again from 0 to 94. It's engines flagging suspicious behavior. The virus total undetected, again 0 to 94. The engines detecting no threats. And finally, the virus total harmless, 0 to 94. The engines are considering the IP harmless. Our dataset composition includes malicious IPs from Abuse IPDBs and trusted IPs from trusted sources like Google, Amazon, and Microsoft to serve as the ground truth. The study of the dataset collected and used in these works reveals distinct patterns between these sources. The IPDB confidence score mostly around 100, which makes it a strong evidence of malicious activities. The reports between 0 and 74 and 906 end users, it's 0 between 1 and 135. It varies widely. The virus total, we have between 0 and 24 malicious detections, many undetected or harmless cases. The reputation goes between minus 127 to 549, which is mostly negative. In post dive, we have risk levels mainly low, around 47%, followed by medium none, which is around 24%, unknown, which is around 19%, and high severity rare and critical was not observed in this dataset. And we have finally IP void, which varies typically between 4 and 11. So the pre-processing of the dataset, We have the data cleaning, which is the initial step involved removing rows with missing values from any of the databases and eliminating duplicate data entry to ensure the dataset quality. Uh, we have the feature transformation, which was the numeric features were normalized using minimal to mask scaling, and the non-numerical category features were also properly encoded for the models. The class balancing with smooch, we addressed class imbalancing using the smooch technique, which is the synthetic minority oversampling technique, and it was applied exclusively to the training dataset. We also had the test set completeness. The test set was intentionally left unchanged. No synthetic data was used in the test set, which must represent real and unpublished data, simulating the model's behavior in real-world situations. So how does our multi-criteria weighted voting works? Our objective was to intelligently combine multiple data sources, overcoming the limitations of complex statistical score, such as poor interpretability, sensitivity to outliers, and inflexibility. The approach is based on classifier combination theory to increase robustness and interpretability. So how does it work? Each data source votes on an IP classification. The votes weight is determined by three metrics, which is the individual performance, it's the accuracy of the source in isolation. Each source votes alone in a verdict, and then we compare these votes with the ground truth. If we have a match in these verdicts, it means that the individual performance of the source is better. We have also the correlation with the ground truth, which is the alignment between the source predictions, which is the output, with the real labels, defined as true labels. And we have the inter-source consensus, which is the sources agreement with other sources in the correct classifications. We also have each source's vote on a verdict, so this vote is compared with the other verdicts of the other sources. And if we have also a match, that is, the source votes the same as the ground truth, we have a consensus. And finally, we have our final decision, which is the three metrics are combined using a weighted average to calculate the final weight for each source. The class with the highest total score, which is the sum of the vote weights, is chosen as the final classification for the IP address. So, our setup and models. The models evaluated were over 7 machine learning algorithms which were analyzed, including the decision tree, random forest, CNN, SVM, and neural networks. The hyperparameters of each model were optimized using grid search with cross-validation to balance complexity and generalizability. Our metrics was the evaluation considered accuracy, F1 score, precision, recall, and, the more crucially, execution time, which was the training time. We also set our architecture to a real-world environment. Our solution was deployed to the natural gateway of the computer science building. We used the TP-Link TL SG105E switch. It has a push mirror function, which we use to mirror about 4 ports to measure its performance over 4 hosts. And we measure its performance and overhead in a real-world scenario. We had real-world traffic coming to a switch, and that's what we analyzed. The high-frequency monitoring its performance in around 7 millimeters, while the database queries are around 3 seconds. It was what takes most time in our scenario, and it is the main source of latency. It only occurs only once per IP address. So the RF models show the highest accuracy, while the DT model was the fastest. And despite RF superior accuracy, its high latency may limit its use in a real-time application. So, based on our results, we chose the Precision tree model because it was the most balanced and recommended choice for production. It is 97.23% faster then random forest, which was about 13.72 seconds, and 19.38 faster than the CNN, which is about 3.95 seconds. Its accuracy of 94.99% is highly competitive, with a reduction of only 0.467% compared to the RF, which was 99.64%. The DT model offers the best trade-off between efficiency and performance, making the most suitable choices for the real-time threat response. We have to consider that in the cybersecurity context, we need a faster response so we can mitigate the threat more efficiently and obviously faster. So, in conclusion, our proposed architecture is highly effective in classifying the risks of IP into allowless, denialless, and suspicious. We're achieving high classification performance with low operational overhead in a real-world environment. Among the models evaluated, the decision tree was selected for the real-time scenarios due to its fast execution and competitive accuracy compared to more complex models like random forests. Our contributions. This solution incorporates a multi-criteria weighted voting mechanism to improve robustness and interpretability, and the creation of a new public dataset to foster research in the area. To our future work, we aim to the creation of a new, more robust dataset with a larger numbers of IP addresses and new databases. We also want to analyze the behavior of the IPs from the collected databases over a time interval using time series analysis so we can identify temporal patterns and predict future risks. We also want to develop an ensemble-based machine learning system combining the strengths of the different models evaluated, which was DT, RF, CNN, and etc., so we can further improve detection accuracy and robustness. And finally, we aim to optimize the fusion of heterogeneous threat data so we can further improve model adaptability and precision. So this is it. Thank you, everyone.